Hello everyone, how are you doing today? I hope once again you are all very well in both health and spirit. So this is the second part of my presentation about the use of DFT-based first principles calculations for the design of poison-resistant catalysts for methane conversion. In the first presentation, or in the previous video recording, I've talked about the formation of carbon on nickel catalyst for methane reforming. In that presentation, I've talked about our study that was published in scientific reports, where we investigated the reason why nickel-based catalysts suffer from carbon formation. So we were able to clarify the bonding mechanism that explains the strong adsorption of atomic carbon on stepped nickel surface, which involves the interaction of atomic carbon with both surface and subsurface layers of stepped nickel surface. I have also shown that substituting the subsurface atom with another element can promote the weaker adsorption of atomic carbon, thereby changing the reaction mechanism of methane decomposition happening on the surface. And from such results, we propose some new models for the catalysis of methane decomposition with the use of nickel-based catalysts. This presentation is the second part where I will be talking about sulfur formation or sulfation on palladium-based catalysts for methane oxidation. I show here one important application of a catalytic methane oxidation. Here is a schematic diagram of gas turbine power generation system. So a gas turbine is a combustion engine that can convert natural gas or other liquid fuels to mechanical energy. This energy then drives a generator that produces electrical energy. Now, experiments have shown that palladium-based catalysts have excellent activity for methane oxidation under net oxidizing conditions. A general consensus suggests that palladium exists in the form of an oxide when methane oxidation proceeds under oxygen-rich conditions and at temperatures below 950 Kelvin. In situ XRD and XPS measurements showed that palladium oxide 101 develops preferentially during the oxidation of pure palladium 100. Its formation coincides with the increased rates of methane oxidation, suggesting palladium oxide oxidation to be responsible for the exceptional activity of palladium-based catalysts for the catalytic combustion of methane. However, palladium oxide suffers tremendously from sulfur poisoning or sulfation of the surface. It is due mainly to sulfur in the form of SO2 contained in the natural gas itself, which is used as an odorizer or from engine lubricating oil in combustion systems. Experiments reveal the formation of sulfides and sulfates on palladium catalysts, which are believed to poison or deactivate the active sites for methane oxidation. So because of this, significant experimental efforts were directed toward understanding the mechanism of sulfur poisoning of a palladium oxide methane oxidation catalyst. So in this contribution, first principles calculations based on density functional theory with van der Waals correction were used to reveal the mechanism of palladium oxide 101 sulfation in relation to the activation of methane. In particular, we identified the mechanistic paths toward SO4 formation or sulfation on the palladium oxide 101 surface and describe how the active sites for methane activation are altered by the adsorption and subsequent oxidation of SO2. We reported our results on this paper entitled Sulfation of a Palladium Oxide 101 Methane Oxidation Catalyst, Mechanism Revealed by First Principles Calculations, which were published in Catalysis Science and Technology in 2019. I show here our slab model of palladium oxide. The monoxide compound palladium oxide is the only known stable oxide of palladium. Its calculated lattice constants are A equals 3.06 angstrom, C over A of 1.77, which are in excellent agreement with those in experiments. This figure shows the side and top views of the palladium oxide 101 surface, which was modeled using a slab with 4 palladium layers in a 1x2 supercell with approximately 12 angstroms of vacuum space. The palladium atoms on the surface are labeled as either 3F or 4F to denote the 3-fold and 4-fold coordinated palladium atoms. which I will respectively refer to in this presentation as Palladium 3F and Palladium 4F atoms respectively. Palladium forms a square planar coordination with oxygen atoms as shown by the red and blue planes in this figure. Palladium 3F is coordinatively unsaturated or CUS with a coordination vacancy on top of the Palladium 3F atom. The oxygen atoms on the surface are also labeled as either 3F or 4F based on their coordination with the palladium atoms, which I will also refer to in this presentation as either oxygen 3F or oxygen 4F respectively. The oxygen 3F atoms protrude out of the surface while the oxygen 4F atoms bond with the subsurface atoms. The coordination plane of the unsaturated palladium 3F atom is perpendicular to the surface, while that of the palladium 4F atom is tilted with respect to the 101 surface. In palladium oxide, palladium atoms are oxidized while oxygen atoms are reduced. As shown by the bar charges reported in this table, the palladium 4F atoms have lost more electrons than the palladium 3F atoms because more oxygen atoms are coordinated to the palladium 4F atom. Correspondingly, more electrons are gained by the oxygen 4F atom than oxygen 3F atom because of the difference in their coordination with the palladium atoms. These observations correspond to the change in the electronic structure of a non-oxide palladium atom as it forms an oxide shown in this figure. Here, the projected local density of states on the D-band of the palladium atom at the step edge of palladium 211 surface, representing a pure palladium metal, and the palladium 3F and 4F atoms of the palladium oxide 101 surface are shown by the blue, black, and red curves respectively. Correspondingly, the sp states of the oxygen 3F and 4F atoms are shown in this figure. With respect to the D-band of the non-oxide palladium 211, there's an emergence of unoccupied states above the Fermi level in the D-band of both palladium 3F and palladium 4F atoms of palladium oxide 101. A broader unoccupied state is seen for palladium 4F atom, corroborating the earlier noted greater electron loss in the Bader charge analysis. In the energy range below -4 electron volts, new states are formed in the D-band of the palladium 3F and palladium atoms with respect to the D-band of the pure palladium atom. These states hybridize with the sp states of oxygen shown in this figure, indicating the palladium D and oxygen sp bonding states. The projected partial charge density plot in this energy range shows the covalent bond between the palladium and oxygen atoms. Interestingly, the projected partial charge density plots in the energy range above the Fermi level show the different characteristics of the unoccupied states of the palladium 3F and palladium 4F atoms. For the palladium 3F atoms, the unoccupied state has a DZZ character, which stems from the presence of an oxygen atom directly below the 3F palladium atom. This unoccupied DZZ state of the 3F palladium atom hints its higher affinity toward electron donation from the sigma-type molecular orbital of adsorbates. Assigning the 3F palladium atom coordination plane as the XZ plane, the corresponding occupied state of the 3F palladium D-band has a DYZ character. On the other hand, for the case of palladium 4F atom, similar analysis indicates that the unoccupied states of its D-band have DXY characteristics. Because the palladium 4F atoms are rectangularly coordinated to 4 oxygen atoms on the XY plane, its DXY orbital is depopulated. Correspondingly, the DZZ orbital of palladium 4F atom is occupied, which is expected to result in a repulsive interaction toward the sigma-type molecular orbital of the adsorbate. As the palladium atoms in the palladium oxide are oxidized, they have higher affinities for electron donation from the adsorbate and reduced tendencies for back donation. By its spatial distribution, the palladium 3F atom DZZ state can facilitate the electron donation, resulting in the greater reactivity of palladium 3F atom compared to palladium 4F atom. Let us look at how palladium oxide 101 surface activates methane. Though the methane oxidation pathway is a subject of an ongoing debate, there's a general consensus that the initial CH bond activation of methane is the main limiting step. This figure shows the optimal adsorption configuration of CH4 on palladium oxide 101 surface. The two CH bonds are coordinated with the palladium 3F atom, while the other two CH bonds are pointing away from the surface. This confirms the earlier predicted reactivity of palladium 3F atom from the analysis of its electronic structure. Considering the identified unoccupied DZZ and occupied DYZ states of 3F palladium atom mentioned earlier, the mechanism of electron donation and back donation between methane and palladium 3F atom can be drawn. The highest occupied molecular orbital of CH4 is a threefold degenerate sigma-type molecular orbital 1t2, as shown in this figure. This filled molecular orbital can donate electrons to the unoccupied DZZ state of palladium 3F. The occupied palladium 3F DYZ orbital can facilitate the back donation to an unfilled sigma star antibonding molecular orbital of CH4. Considering the phase and spatial distribution of the unfilled CH4 molecular orbitals, the 2t2 molecular orbital can facilitate the back donation from the unoccupied palladium 3F DYZ orbital as shown in this figure. This back donation results in the weakening of the two CH bonds coordinated to the palladium 3F atom. We found that these activated CH bonds are elongated by 21 milliangstrom with respect to the gas phase CH bonds of methane. The charge density difference plot in this figure shows an accumulation of charges between CH4 and the palladium 3F atom, which is attributed to a dative covalent bond. So let us now look at the energy needed to break the activated and non-activated CH bonds of methane. This figure shows the energy profile for the dissociation of methane into CH3 plus H. At the final state, CH3 bonds with palladium 3F atom, while the oxygen 3F atom acts as the hydrogen acceptor, forming a CH3 palladium 3F and H oxygen 3F moieties. The transition states were calculated using the dimer method, with the initial direction along the dimer generated based on the initial and final states. The activated and non-interacting CH bonds required activation barriers of 0.66 electron volt and 1.72 electron volts respectively. This confirms the weakening of the CH bonds coordinated with the palladium 3F through back donation to the CH4 sigma star antibonding molecular orbital. Following the initial activation of methane, DFT-based microkinetic modeling and kinetic isotope studies reported in the literature found that the subsequent reactions with oxygen follow the Mars-Van Crevellin mechanism, where the oxygen atoms from the substrates are used to produce carbon dioxide and water. So the results from the previous slides have shown that the 3F palladium atom and 3F oxygen atoms on palladium oxide 101 surface play important roles in the activation of methane. It can be argued that blocking these active sites with other adsorbates can decrease the activity of the catalyst for methane activation. I show in this figure the adsorption configurations of O2, SO2, SO3, and SO4 together with CH4. It can be seen that the adsorption of SO2, SO3, and SO4 molecules involve both the 3F and the 4F palladium atoms, suggesting a possible poisoning of the palladium 3F site. SO2 forms two oxygen palladium 3F bonds and one sulfur palladium 4F bonds on the surface with an adsorption energy of negative 1.74 electron volts. This value of adsorption energy is more than 10 times greater than that of CH4, which is only about negative 0.16 electron volt. This explains why sulfur poisoning is still prominent despite its very low concentration, which is only around 1 ppm or less, under typical experimental conditions. SO3 and SO4 have similar bonding characteristics on the surface, where they form bonds with two palladium 3F atoms and one 4F palladium atom. The stabilities of these adsorbed species were computed by calculating their free energies of adsorption with respect to gas phase CH4, O2, and SO2, and the clean palladium oxide 101 surface as shown by these equations. The asterisk denotes surface-bound species, while the molecules with no asterisk denote the gas phase species. The chemical potentials mu of gas phase species were computed by adding the DFT calculated total energy, the zero-point vibrational energy, and the temperature and pressure dependent parts of the chemical potential. The temperature dependence of free energies for the condensed phases was shown to have no significant impact on constructing phase diagrams and is thus ignored in this calculation. I show in this figure the phase diagrams with respect to clean palladium oxide 101 surface denoted by asterisk to indicate an empty site. In the surface with adsorbed O2 shown by the red region, SO2, yellow region, SO3 which is not shown here, and SO4, the green region, in the given range of SO2, O2, and CH4 chemical potentials, which are translated into a pressure range at temperature equal to 400 degrees Celsius. Essentially, the figure shows the most stable, that is, the one with the lowest free energy, adsorbed species for a given chemical potential of gas phase molecules. The typical experimental conditions is indicated by the circled X symbol. It can be seen that for the first two phase diagrams that only show the chemical potentials of CH4 and either O2 or SO2, the bare surface is the most preferred. However, in the phase diagram that considered both SO2 and O2 chemical potentials, the SO4 decorated surface is the most thermodynamically preferred surface. These results explain why under typical experimental conditions for methane oxidation, where the O2 and SO2 partial pressures are about 0.20 atmosphere and 5 × 10⁻⁻⁶ atmosphere respectively, the SO4 decorated surface of a palladium oxide 101 is detected. So, considering that the SO4 decorated surface is highly favored under typical experimental conditions, it is imperative to describe the reaction mechanism of this formation from SO2. The figure in this slide shows SO2 oxidation to SO4 on palladium oxide 101 via the iliradial mechanism shown by the red path followed by the black path, the Lemure-Hinshelwood mechanism shown by the black path, and the Mars-Van Crevelin mechanism shown by the blue path. Briefly, in the iliradial mechanism, only O2 adsorbs on the surface, after which SO2 reacts with adsorbed oxygen. In the Lemure-Hinshelwood mechanism, both SO2 and O2 first adsorb onto the surface before reaction takes place. Finally, in the Mars-Van Crevelin mechanism, SO2 forms a chemical bond with the surface oxygen atoms of palladium oxide 101, generating an oxygen vacancy site upon the production of SO3 and SO4. I show in this figure the free energy landscape for these reactions. The Gibbs free energy of adsorbed species was calculated by adding the zero-point vibrational energy and vibrational energy change for temperature increase from 0 to a particular temperature and subtracting the vibrational entropy. The free energies were referenced to the chemical potentials of gas phase SO2 and O2 and the free energy of the slab. This figure shows the energy profiles for temperatures of 0 Kelvin to show the energy profile without entropic corrections, and 400 degrees Celsius, which is a typical temperature in experiments where CH4 conversion is observed. It can be seen from the figure that compared to the 0 Kelvin case, the free energy profile at 400 degrees Celsius displays higher activation energies and more endothermic reaction energies. This is due to the large increase in the entropy of gas phase O2 and SO2, which means that there are more negative chemical potentials which are used for reference energy. However, considering the large increase in the temperature from 0 Kelvin to 400 degrees Celsius, the rate constant for the elementary steps are expected to increase largely, as described by the Arrhenius equation. Let us first analyze the energy profile in the 0 Kelvin case. As shown by the red curve in the iliradial path, The activation of O2 requires an activation barrier of approximately 1.68 electron volt. The transition state is shown by TS1. Subsequent to the dissociation of O2, SO2 from the gas phase can form an SO3 plus oxygen coadsorbed state, where SO3 binds at the 4F palladium atom with a planar structure. Further SO bond formation between SO3 and oxygen toward the SO4 product proceeds thermodynamically downhill in energy. As shown in this figure, the tridentate SO4 is the most stable, followed by the bidentate and monodentate structures. The reaction energy for the overall process of adsorbed SO4 formation from the reference state is negative 4.27 electron volts. In the Langmuir-Hinshelwood path, SO2 adsorbs on the surface with greater adsorption energy than molecular oxygen. The coadsorbed state, SO2 plus O2, is only slightly downhill in energy from adsorbed SO2 state. This state is expected to have a lower energy in the zero coverage limit as the lateral interaction between SO2 and O2 becomes negligible. From the SO2 plus O2 coadsorbed state, the activation of O2 requires a higher energy barrier of 1.79 electron volt compared to its dissociation without a coadsorbed SO2. This indicates the contribution from the lateral interaction between SO2 and oxygen atoms. The subsequent SO bond formation toward SO3 plus O state is inferred to be barrierless as the optimization of coadsorbed SO2 plus 2 oxygen atoms readily yields SO3 plus oxygen. The blue curve in this figure shows the Mars-Van Crevellin mechanism where the oxidation of SO2 required the formation of oxygen vacancies on the surface. The adsorbed SO2 diffuses to a nearby oxygen 3F atom to form an SO3 species. This process is 0.71 electron volt endothermic. From here, the adsorbed SO3 diffuses to the adjacent oxygen 3F site, forming an oxygen vacancy at adsorbed SO4, which is only about 0.06 electron volt endothermic. Finally, a slightly exothermic process proceeds, where another oxygen vacancy is formed as SO4 adsorbs in a tridentate structure on 3 coordinatively unsaturated palladium atoms as shown by this figure. The overall process for this Mars-Van Crevellin mechanism has a reaction energy of negative 1.0 electron volt with respect to the reference state. These results show that despite the highly exothermic SO2 oxidation on palladium oxide 101 surface via the Illyridial and Langmuir-Hinshelwood mechanisms, its kinetics can be limited by the high barrier for O2 dissociation. On the other hand, the Mars-Van Crevellin mechanism has low exothermicity for the overall SO2 oxidation process, but is expected to promote more favorable kinetics because of the relatively facile elementary steps. In the 400 degrees Celsius case, it can be noted that the energy profile gives the same preference towards the Mars-Van Crevellin mechanism. The Illyridial and Langmuir-Hinshelwood paths are still limited by the earlier noted activation of O2 molecule. Similar to the 0 Kelvin case, the formation of SO3 and SO4 on the surface proceeds downhill in energy subsequent to the activation of O2 for both the Illyridial and Langmuir-Hinshelwood mechanisms. So let us now look at how we can modify the properties of palladium oxide to avoid sulfur poisoning. Experiments suggest that alloying palladium oxide with other metals can potentially address the problem of sulfur poisoning, in addition to improving the activity and stability of palladium catalyst for methane oxidation. However, the choice of the alloying metal to palladium oxide has been challenged by the lack of theoretical studies in the literature that systematically screen the potential alloying metals or impurities that favorably alter the properties of palladium oxide to mitigate sulfur poisoning and promote better activity towards methane oxidation. So in this work that we have recently reported in Catalysis letters entitled Adsorption of CH4 and SO2 on unsupported palladium 1-X mx oxygen 101 surface, we use first principles calculations based on dispersion-corrected density functional theory or DFT-D3 to systematically screen the metal impurities M, where M is a transition metal, on a palladium oxide 101 surface to identify the palladium 1-X MX Oxygen 101 catalysts that promote the favorable adsorption energies for CH4 and SO2, describe the effect of these impurities on the electronic properties of palladium oxide, and compare the thermodynamically stable surface states of palladium oxide 101 and palladium 1-X MX Oxygen 101 at typical experimental conditions. To model the alloyed surface, one surface palladium atom from either the 3-fold or 4-fold side was replaced with a metal impurity M, providing an M is to palladium surface ratio of 1:3, as shown in this figure. In the precursor-mediated mechanism for methane activation, CH4 first adsorbs on the surface, and the resulting molecularly adsorbed state serves as a precursor for CH bond cleavage. Thus, the adsorption energy of CH4 can be used as an approximate descriptor of activity for methane activation. That is, the desired catalyst should promote a stronger adsorption of CH4 compared to pure palladium oxide 101 surface. Similarly, as our previous work has shown that the sulfation of palladium oxide 101 surface is initiated by the strong adsorption of SO2, its adsorption energy can be used as a screening descriptor for sulfur poisoning. The desired catalyst is the one that promotes a weaker adsorption of SO2 than on pure palladium oxide 101 surface. So to this end, the adsorption energy of methane was plotted against the adsorption energy of SO2 for different metal impurities M at the 3-fold and 4-fold sides on the alloyed surface. Here, the desired region is shown by the green shaded region, which corresponds to stronger CH4 adsorption and weaker SO2 adsorption on the alloyed surface than on pure palladium oxide 101 surface. For M substitution of the palladium 3F side, an approximate linear trend in the adsorption energies of methane versus SO2 can be seen. As I've discussed earlier, analysis of the electronic properties of the palladium oxide 101 surface points to the importance of palladium 3F atom in both the activation of CH4 as well as the adsorption of SO2. On the other hand, for the M substitution of the 4F palladium side, the plot is more scattered. However, it is noted that for both the palladium 3F and palladium 4F substitution cases, the adsorption energy of methane is stronger for all M transition metals compared to pure palladium oxide. Interestingly, the desired adsorption energies for CH4 and SO2 are achieved for M equals gold case, where the gold atom substitutes the 3F palladium atom. So we compare the electronic properties of palladium oxide and palladium gold oxide alloy. I show here the local density of states projected on palladium 3F atom on the surfaces of palladium oxide and palladium gold oxide alloy. The inset figure shows the partial charge density plot projected on the peak shown by the arrow for the case of palladium oxide. Similar partial charge density plot is shown for the palladium gold oxide alloy at the peak denoted by another arrow. This shows that the unoccupied state of palladium 3F atom on palladium oxide has retained its DZZ characteristic on palladium gold oxide alloy. As mentioned earlier, such an occupied DZZ orbital plays a major role in the adsorption of methane. Moreover, it can be noted from this figure that the DZZ peak of palladium gold oxide alloy is upshifted and more unoccupied with respect to pure palladium oxide, indicating a greater tendency for charge donation from the field CH4 sigma orbital. This explains the calculated stronger adsorption of CH4 on palladium gold oxide alloy than on pure palladium oxide. Now I show in this figure the D state of gold and sp states of oxygen 3F and oxygen 4F atoms of the palladium gold oxide alloy. The inset figures show the partial charge density plots projected on energy range bound by the bracket or at the peak shown by the arrow. At the low energy range far from the Fermi level, a strong hybridization between the gold D and oxygen sp states is noted, suggesting a strong anchorage of the oxygen atom on the surface provided by its neighboring oxygen 4F and oxygen 3F atoms. Interestingly, while oxygen substitutes the 3F palladium atom, the DZZ state is occupied, contrary to the unoccupied DZZ of a palladium 3F atom that I have mentioned earlier. Because the gold atom on palladium gold oxide alloy is not seen to interact with the oxygen atom below it, The depopulation of the DZZ orbital observed for the 3F palladium atom of palladium oxide is not seen for gold on the palladium-gold oxide alloy. This yields the DZZ orbital of gold occupied. As I have mentioned earlier, having an occupied DZZ state is characteristic of a surface 4F palladium atom. Thus, this alloyed surface model provides a row of 3F palladium and 3F gold atoms with alternating unoccupied and occupied DZZ states respectively. I show in this figure a comparison of the adsorption structures of CH4, O2, SO2, and SO4 with corresponding adsorption energies shown in the graph. Vibrational frequency calculations show the absence of imaginary frequencies for these adsorption structures, while the calculated adsorption energies for methane are in agreement with other studies. As I have shown in the previous slides, an adsorbed SO3 is not thermodynamically favored at typical experimental conditions and is thus neglected in this current work. Similarly, it was shown that the formation of dissociated O plus O adatoms on palladium oxide is thermodynamically less stable than for the molecularly adsorbed O2 and is kinetically limited by the high activation barrier for O2 dissociation. So I do not show the adsorption of atomic oxygen here. As shown in this figure, CH4 adsorbs at the 3F palladium site for both the palladium oxide and palladium gold oxide alloys surfaces. As shown in this figure, CH4 adsorbs at the 3F site for both the palladium oxide and palladium gold oxide alloy surfaces. The same average CH bond lengths were noted for the two quote-unquote activated CH bond lengths pointing toward the surface. O2 molecule changes its adsorption structure from a bidentate bonding on palladium oxide to monodentate bonding with the 3F palladium atom of a palladium gold oxide surface because the occupied DZZ of gold exerts a repulsive interaction with the filled O2 molecular orbitals. SO2 also changes in its adsorption structure as it transforms from the tridentate structure on palladium oxide to a bidentate structure on palladium gold oxide surface. For these two surfaces, SO2 retains its characteristic in which one oxygen binds with the 3F palladium atom with an occupied DZZ orbital and the sulfur atom binds with an oxygen atom with occupied DZZ orbital, which is a 4F palladium atom for palladium oxide and gold for the case of the palladium gold oxide surface. For SO4, it retained its adsorption configuration for the two pristine surfaces. Now I show in this slide similar phase diagrams that I've shown earlier. The solid line in the phase diagrams denote the case of the pure palladium oxide that I've shown earlier, while the dashed lines denote the case of palladium gold oxide surface. And again, the circled X symbol shows a point in the phase diagram at typical experimental conditions. Based on the two figures in the upper panel, a stable CH4 covered surface is favorable only at high CH4 partial pressures, which is greater than 10 atmosphere for temperature of 400 degrees Celsius. This is because of the weak adsorption of CH4 on the surface. An SO2 decorated surface is easier to form on pure palladium oxide than on palladium gold oxide surface, requiring an SO2 partial pressure greater than approximately 0.5 atmosphere at a temperature of 400 degrees Celsius. However, it is noted that at typical experimental conditions, the concentration of SO2 in the input gas is very small, yielding an SO2 partial pressure of only about 5 × 10⁻⁻⁶ atmosphere at 400 degrees Celsius. An oxygen-decorated surface is also easier to form on palladium oxide than on palladium gold oxide surface. However, an O2 partial pressure much greater than 1 atmosphere is required to achieve this surface state for pure palladium oxide. The third figure here shows that at typical experimental conditions, an SO4 decorated surface is the most stable surface state for pure palladium oxide, as I have previously discussed. Interestingly, because of the shift in the phase transition lines for the case of palladium gold oxide alloy surface, with respect to pure palladium oxide, the pristine surface is the most stable surface state for the case of the palladium gold oxide surface at typical experimental conditions. This indicates that the thermodynamic preference of palladium oxide 101 to form a stable SO4 decorated surface at typical experimental conditions is suppressed by introducing gold impurities on the surface. So these results provide the first theoretical investigation into the use of metal impurities to tune the catalytic properties of palladium oxide to promote the desired activity and selectivity toward methane oxidation and sulfur poisoning. While the pure palladium oxide 101 surface is more stable than the identified palladium gold oxide surface, the literature reported the successful synthesis and fabrication of various gold-doped palladium oxide and gold-X palladium alloys for industrial and biological applications. Nevertheless, the discovery of other specific or combination of additives or impurities that are both stable and active for the desired reactions still remains to be a great challenge in catalyst design. So I hope that this work will stimulate further research interest into the synthesis and design of novel sulfation-resistant materials for methane oxidation. So with that note, thank you very much for your very kind attention, and I wish you all the best for your research endeavors.